Good evening, everyone, and thank you for joining us online. My name is Professor Moira O'Brien, and I have the pleasure of being the Dean of the Faculty of Science here at the University of Melbourne. It is indeed my pleasure to welcome you to the second lecture in the Science at Melbourne Dean's Lecture Series for the year. I would like to start by acknowledging the traditional owners of the land where I speak to you from today, and they are the Wurundjeri people. I also acknowledge the traditional owners of the land our online audience is situated on, and acknowledge that Indigenous Australians have been the custodians of the lands and waterways of Australia for thousands of years. I acknowledge and respect the Aboriginal and Torres Strait Islander people as this country's first scientists with deep and enduring knowledge of the lands, the waters, and the skies. And I pay my respects to elders past and present, and I particularly welcome any First Nations people joining us tonight. Our Dean's Lecture Series is an annual calendar of events that proudly shares the faculty's knowledge and scientific curiosity. Last month, we launched the series with a vibrant panel on colour, light, and energy. 2 more public lectures will be hosted throughout the year as part of the series, covering exciting scientific research and theories, and we hope you will continue to join us. Tonight, we're here to talk about carbon. Let's face it, it has a bad rap. Globally, as we battle the monumental challenge of curbing climate change, we are looking at ways to reduce carbon excess in the atmosphere. What can we learn from past climates to inform future decision-making? What needs to change in the energy sector to reach net zero carbon? And how do we expect the climate to change when net zero carbon is achieved? Our dynamic panel of experts will unpack what the transition to meet net zero carbon looks like. Tonight's panel consists of 3 fantastic academics: Dr. Vera Korasidis from the School of Geography, Earth and Atmospheric Sciences, Dr. Andrew King, who is also from our School of Geography, Earth and Atmospheric Sciences, and Professor Michael Brear, who is the Director of the Melbourne Energy Institute. We are also delighted to have Professor Todd with us this evening. Todd is the head of the School of Geography, Earth and Atmospheric Sciences, and he will take the reins as moderator. Todd is a key investigator in the Australian Research Council's Centre of Excellence for Climate Extremes, where his research focuses on weather-climate interactions and state-of-the-art atmospheric modelling. Prior to joining us at the University of Melbourne, he held research scientist appointments at the National Centre for Atmospheric Research in the United States. He is a fellow and past president of the Australian Meteorological and Oceanographic Society. Todd's current research focuses on a broad range of topics that help inform weather predictions and climate, including climate extremes, storms, fire weather, weather prediction, tropical meteorology, and aircraft turbulence. We are very lucky to have Todd here to moderate what will be an insightful discussion. Thank you all again for joining, and with pleasure, I hand over to Todd.
Thank you, Moira. Thank you for that nice introduction. My name is Todd Lang. As Moira said, I'm from the School of Geography, Earth and Atmospheric Sciences here at the University of Melbourne in the Faculty of Science. I'd also like to acknowledge that I live and work on the unceded lands of the Wurundjeri people of the Kulin Nation and pay my respects to their elders past and present. It's my pleasure to welcome you to this Faculty of Science Dean's Lecture on carbon in the atmosphere. Is it all bad news? For those of you who are joining us online, this webinar is being recorded and will be available online shortly through the Faculty of Science website. This link will be also emailed to everyone who registered, and so those who are unable to join us tonight will be able to watch it. So we have 3 speakers tonight, and each will give a short presentation, and then I'll ask them some questions and moderate a discussion. Then I'll be opening up to the online audience for questions. I encourage you to post questions in the Q&A function in the For the Zoom at the bottom of the screen, the chat is disabled, so please only use the Q&A function. I'll be reading those questions and directing them to a specific panel member, but if you have a question for a specific panel member, please make that clear in your question. So let's talk about carbon. Carbon is all around us. It's almost 20% of the human body. It's up to 50% of trees. It's a significant part of our atmosphere, being the fourth or fifth most abundant chemical in our atmosphere. It's been a critical part of our modern society, supporting the Industrial Revolution and the modernisation of our society around us. But carbon and carbon emissions have had significant negative consequences on our climate, our environment, and threatens the future habitability of our planet. Over my lifetime, carbon dioxide in the atmosphere has increased by almost a third, by about 100 parts per million. And also global mean temperatures have increased by almost 1 degree. We've experienced significant changes to our weather patterns and enhanced extremes. So it is clear that rapid decarbonisation is required to mitigate against the most significant climate impacts. So let's come back to this original question. Is it all bad news? Well, this doesn't mean to imply that climate change is a good news story. It very much is not. But today we are talking about hope, and hope for the future. The opportunities to reduce emissions and mitigate climate change and take our country to net zero, and that's how we're going to get there. So I have 3 wonderful speakers today who will give us hope and speak about how we'll get to net zero and what will happen to our climate. I'll briefly introduce them now. Dr. Vera Korasidis is an Elizabeth and Vernon Pusey Fellow and lecturer in the School of Geography, Earth and Atmospheric Sciences at the University of Melbourne. Prior to her current position, she's a postdoctoral fellow at the National Museum of Natural History at the Smithsonian Institute in the United States. Her research seeks to improve our understanding of floral response to warm climatic events that may provide a deep time analogue for future climate change. Professor Michael Brear is a mechanical engineer and the director of the Melbourne Energy Institute at the University of Melbourne. MEI, the Melbourne Energy Institute, facilitates the university's research on the technical, economic, environmental and societal impacts of energy. Prior to commencing at the University of Melbourne, Michael worked for ICI Australia, which is now Orica. He then undertook graduate studies at Cambridge University and postdoctoral research at the Massachusetts Institute of Technology, MIT. Dr. Andrew King is a senior lecturer in climate science, also in the School of Geography, Earth and Atmospheric Sciences. He gained his undergraduate degree in meteorology from the University of Reading in 2011 and PhD in climate science from University of New South Wales in 2015. Since then, he has worked at the University of Melbourne as a postdoctoral fellow, an ARC DECRA fellow, and a lecturer and now senior lecturer. Andrew is interested in climate change science, extreme events, prediction and projections, and climate change impacts. So welcome to all 3 of our panelists, and I'll invite Vera to start her short presentation.
Excellent. Thanks, Todd, and it's wonderful to be here. So for tonight, I'm going to offer you all a geologist's perspective on carbon. So where exactly in our Earth is carbon? So the largest reservoir, to the delight of geologists, is of course rocks and sediments. And so this carbon is really important in long-term climate change. The smallest reservoir, the atmosphere, however, plays an incredibly important role in short-term climate change on the order of decades to thousands of years. But the one thing both these systems have in common is that their climate is controlled by the carbon cycle. And this cycle involves the removal of CO2 from the atmosphere through rock and silicate weathering. You then have the precipitation of calcium carbonate, and due to plate tectonics, this is eventually subducted, melted, and then re-released into the atmosphere as CO2. And this entire cycle, the carbon cycle, is what's controlled the Earth's climate for over 1 billion years. And so there's lots of geological evidence in favor of the fact that it's actually CO2 that's driving Earth's climate through time. Next slide, please. So how has the Earth's temperature changed over the last 17 million years? Well, this graph, which shows changes in temperature from around 65 million years ago on the left to the present day, all the way on the right and into the future, demonstrates that the Earth's temperature has fluctuated considerably. The warmest interval occurs during the Eocene, which is around 50 million years ago, and the temperature since then has progressively become cooler and cooler until more recently, human activities have led to an increase in temperature again. But the wonderful thing about studying rocks and sediments is that they provide us with a really unique insight into the Earth's past climate. And when we look at the projections going forward, which Andrew and Michael will discuss, it's suggesting that we'll see conditions on Earth return to what we experienced around 50 million years ago. So we can actually look to the past to help us understand what the Earth might look like. So in order to determine this, I've been focusing on a really interesting period in Earth's history, known as the Paleocene-Eocene thermal maximum, or the PTM, which I've highlighted on this figure. And you'll see it's marked by this really sharp increase in temperature that occurred around 56 million years ago. Globally, temperature increased by around 4 to 8 degrees, and this previous increase was due to a rapid injection of CO2 into the atmosphere. Next slide, please. So part of my research, which I've been conducting in collaboration with the Smithsonian Institution, has been to try to discern how plants previously responded to this rapid increase in CO2 and temperature. So over the past 3 summers, I've headed out to Wyoming and I've been digging up leaves and pollen to try to determine what happened. And what we found is that before this PTM event, Wyoming was once a warm temperate forest. The leaves and pollen we've recovered are today produced by plants that thrive in the swamps of Georgia and Florida. So very, very wet, swampy. We've also found some alligator fossils, all in favor of this hypothesis. Fast forward 10,000 years, which is geologically quite rapid, into the PTM, and all of a sudden we start finding new leaf types and pollen types that are instead produced by plants, including palm trees and legumes, that instead suggest that seasonally dry tropical forest prevailed. So within a mere 10,000 years, that previous increase in CO2 and temperature led to mass plant migration, huge losses of soil organic carbon, and a complete turnover. So to put it into a context that may be more familiar with us here in Melbourne, it's as if the flora and climate of southern Queensland suddenly, within 10,000 years, appeared in Melbourne. So by studying the past, what this actually suggests is that the next time CO2 increases, and as it does today, we can expect in some parts of the world for temperatures to increase, for climates to become drier. We're going to experience mass plant migrations if possible, and along with that, of course, animal migrations as well. So I think this offers us an opportunity, I suppose, to really think hard about whether we are prepared to physically move like these trees did, or can we alter our habits today in order to prevent some of these huge changes that may occur in the future. So thank you.
Thank you, Vera. I'd like to invite Michael now to start his short presentation.
Good evening, everyone. Thanks, Vera, for that lead in. It makes what we're working on at the moment very much in perspective, and it's fascinating overall. So I'll talk briefly about Net Zero Australia, which is a project that Melbourne Uni has been running for the last 2 years or so with University of Queensland, Princeton University, and a management consultancy called the Nous Group, who've been terrific collaborators. It's been a wonderful project to date, and we're still powering on. I'll go to the next slide. We're going to just very briefly talk about some of the stuff we've been doing, but in a nutshell, what we've worked on with a whole bunch of organisations, with a whole bunch of industry, environmental NGOs, other NGOs, industry and government. We've been working out, broadly speaking, what would it take for Australia to get to net zero by mid-century. And we can say, in a nutshell, and it rolls off the tongue pretty easily, we need to do 3 things, but each one of these 3 things is actually immense and complicated. So the first of the 3 things is that we need to deliver an energy transformation that's unprecedented in scale and pace. The second thing we need to do is transform our exports as an essential contribution to global decarbonisation. And the third and often ignored contribution is we need to invest very considerably in our people and our land. And we need to reduce impacts by those investments and also share what are hopefully very large benefits. But if you look at each of those three things on the right-hand side and break it out into further detail, these are the kinds of things we're talking about doing. Of course, we need a massive amount of renewable energy, and we need to roll it out at an unprecedented speed, much faster than we're going already. And we've done tremendously well over the last 20 years on renewables. But on top of that, we need to put an awful lot of other things in. We need a lot more batteries, we need pumped hydro, we need even a little bit of gas-fired firming, although in terms of overall greenhouse gas emissions, they're a negligible source of emissions, but provide energy services the batteries and other forms of storage can't quite provide. We need to do electrification right across the nation. You know, we need to be having many people driving, if not everybody driving electric cars, but that's not everything. We need induction cookers in our homes, we need heat pumps, we need more public transport, so on and so forth. And in addition to all of that enormous investment in renewables and electrification, we do need carbon capture and storage, because there are some things that can't easily be replaced with renewables and electrification. For example, cement making, or the fuels that are emitting CO2 while we fly our aeroplanes, and so on and so forth. So we see CCS as a complement and a necessary complement to very large renewable investments. And of course, we need to connect all these things up with transmission and distribution. The whole thing's going to cost literally trillions of dollars, but we're already spending trillions of dollars, have done over the last 30 years on our energy system. We'll have to spend more, but we're already spending trillions of dollars on the last 30 years, and we would spend trillions of dollars even if we didn't go for net zero and ignored the greenhouse challenge ahead anyway. So you can see many things that need to be done overall. I'll move on to the next slide though, because there's two other things in particular I want to talk about, particularly to students and many of you online. That is, one very important part of this, an essential part of this, is we're going to need a lot more people working in this sector. So here are two plots on the left-hand side, on the right-hand side, of the number of workers in the sector for a bunch of different scenarios. So the blue line along the bottom is the reference scenario. That's a scenario where we forget about greenhouse gas emissions and just keep doing what we're doing. And Australia will continue to have about 100,000 people in the energy sector in that scenario. But no matter which way you cut it, if you go to any of these net zero scenarios that we've defined in this study, and I won't go into the details, but they're all variations of net zero scenarios, you see very large growth of employment. And that's roughly 1/3 university graduates and 2/3 TAFE graduates. So great opportunities for students doing STEM pathways in this sector. There's going to be very large demands for people undertaking STEM, but not just STEM, project management, law, finance, many areas. And of course, not just university graduates. Indeed, most graduates will be from TAFE schools rather than universities, but great opportunities for young people overall. Next slide, please. And finally, one thing we're going to have to think about very carefully, amongst many things, is the impacts of our energy system on biodiversity and our natural ecosystems. Here's just one shot of the map of Australia, one potential future of Australia, where you can see what those big black sort of incomplete circles are. Massive solar farms that are effectively generating green hydrogen for export to our industry partners. You can see black lines all across Australia. You can see dots in the middle of the Bass Strait. That's offshore wind. There are wind farms, there are solar farms, there's onshore, offshore wind transmission all across the country. And those green areas are specific parts of the nation that are key biodiversity areas. But the integration of biodiversity and the energy system is a very complicated and very important problem, because if we don't get it right, we risk solving the climate change problem, but exacerbating the biodiversity problem. Thanks, Todd. That's me done.
Thank you, Michael, for that interesting presentation. And I'll invite Andrew to speak to us now. Thank you.
Thanks, Todd. And thanks, Vera and Michael, for your interesting presentations. Next slide, please. So, as Michael highlighted, we've got a lot of work to do to really reach net zero emissions. And I really wanted to highlight this as well, just by showing this graph of global annual carbon dioxide emissions since 1960. And you can see, even though there's a lot of talk about net zero emissions, our emissions have gone up in the last 60 years. They've more than doubled, and they're at roughly record high rates. And we need to get those lines down to zero to actually reach net zero emissions. So we're a very long way off net zero emissions at present, despite all the discussions about net zero. The problem is that the global temperature responds to increases in carbon dioxide in the atmosphere. And we know that the more we emit carbon dioxide, the more we warm the planet. The rate of global warming is roughly proportional to the rate of our carbon dioxide emissions. So we're warming the planet at roughly a record rate, at least in the modern era. But it also means that if we were to get down to net zero emissions, we would probably stop warming the planet as a whole. Next slide, please. So I'm just going to talk very briefly about the consequences of net zero emissions in terms of the climate. But just to introduce that, this is a map showing observed temperature changes across the globe since 1950. And you can see, even though we've warmed the planet by a bit over 1 degree Celsius, some parts of the planet have warmed faster than others, particularly the Arctic and northern high latitude regions have warmed very quickly. And the land has warmed faster than the ocean, which means that most people have experienced more warming in their locations than the global average that we often talk about in reference to the Paris Agreement, for example. The land warms faster than the ocean because water takes a lot of energy to warm up. It has what we call a very high specific heat capacity, and because the oceans can mix down heat to some depth, whereas the land can't do that. It doesn't really move in the same way. So the land responds very quickly to that increase in carbon dioxide in the atmosphere. The oceans respond much more slowly. But what would happen if we reach net zero emissions? Next slide, please. So I'm showing the very same map, actually, because it's quite hard to for us to tell what would happen beyond net zero emissions. We don't actually have very many climate model simulations that explore this, but essentially what we expect to see is that the ocean would catch up to the land. We'd expect under net zero emissions, the global average temperature would roughly stabilize. We wouldn't warm the planet any further than we have to the point when we get to net zero emissions. The land would cool down and the oceans would warm up. And that has lots of consequences. It means that most people would experience cooling, but our ocean ecosystems would experience continued warming, perhaps for centuries to come. I'll leave it there. Thanks.
Thank you, Andrew. And I think now it's time for our panel discussions. And so we can close the PowerPoint presentation, and if our panelists can all turn their cameras on, and I'm going to ask you all a few questions. And for those of you who are online, please put your questions in the Q&A, and we will try and get through them all later in this session. So my first question is actually for Vera. So Vera, your work is very much focused on understanding the past to help us understand the likely future. And you showed some really interesting things about how you use fossil plants to understand past climate changes. How exactly do you use fossil plants to understand the past climate and past temperatures? What techniques are you using?
Thanks, Todd. So there's a number of different techniques we use to try to use fossil plants to infer temperature. And the wonderful thing about plants in general is that they require really specific climatic niches. So for example, palm trees can't grow in areas today where the soil freezes at some stage of the year. Other trees have deciduous habitats in order to help deal with snow cover. So we use the modern requirements of plants today to then infer what must have been occurring in the past. And the way we do that is we literally compare the fossils we uncover, whether it be leaves or pollen, with modern examples. We can then use the similar shapes of the leaves, their chemistry potentially, and things like that to then make that connection between the past and the present. I will say there is one caveat. Obviously, the further back in time we go, the more difficult that is to do, because plants obviously across time have evolved and gone extinct. So it works really well for around the last 100 million years. But once we start going back 300-400 million years, it's starting to get a little bit more difficult to make that connection.
Great, thank you, Vera. It's really interesting, and you showed this graph of past climate changes over tens, hundreds of thousands of years. And I guess I've got a question for Andrew to follow up on that. We've seen these past climate changes over tens of thousands of years, but what we've observed over the last 100 years has been a very rapid change due to that rapid increase in carbon dioxide emissions. And this rapid change suggests that climate mitigation and emission reductions are really urgent. So why does it matter if we meet net zero in 2050 or 2060 or 2070? Why does that matter to us? Does it matter at all?
It does matter. The sooner we reach net zero emissions, the sooner we stop warming the planet further. So if we delay reaching net zero emissions, we're more likely to have gone over the global warming levels associated with the Paris Agreement. We may get past 2 or even 2.5 degrees of global warming. And we know that that would have really bad consequences in terms of extreme events, in terms of ecosystem biodiversity loss. So the sooner we reach net zero emissions, the sooner we kind of start correcting for the human influence on the climate and start undoing some of the damage that we've done.
Right. Thank you. So I guess it's critical that we reach net zero as soon as possible. And Andrew showed a graph in his presentation that showed that emissions are still increasing. So Michael, you spoke about the 3 things we need to do to reach net zero, but it seems like we've got a long way to get there. Are we on track? And if not, how do we actually make that happen? How do we accelerate progress here?
You're dead right, Todd. We're not on track, and Andrew showed that very clearly. And the task is extremely large. It's an immense task, and it's a task which all of us need to own. It's can be a tendency where we, for example, say the latest government of the day isn't doing enough. Now, that's true of all governments of the day, probably everywhere on the planet, and has been true for the last 20 years. So we do need much improved and much greater urgency from our political leaders, but also from our governments, from our businesses, but also from our community groups, but also from us individually. So, at this university, we need to walk the walk, not talk the talk only, and we're doing that. But that's true of us at home, individually, and so on and so forth. So this is an enormous challenge, but it is also a challenge. It can be quite dispiriting when you look at the enormity of it. But a good scientist is always trained in first year to reference a number to a number that has meaning to you. So that might be how many calories fewer I need to eat relative to how many I currently eat today, or it might be how many solar farms we need to build relative to those we do today. And when you normalise these, the tasks ahead, like those jobs growths, for example, we have created those number of jobs, for example, in different sectors over the last 20 or 30 years. We have done that before. We've done that in the public service. We've done that in various sectors or not. We have created a new energy export sector in the last 10 to 15 years called liquefied natural gas. And that was without it being an urgent an urgent environmental requirement. And we have invested trillions of dollars in energy before, and we do have the money to do so. So I think when you look at these numbers and you reference them against what the best of what we have done, I actually think you see that it's achievable.
Great, thank you, Michael. I guess a follow-up question. You've highlighted now that it's not only it's a policy challenge, it's a skills challenge, but it's also a technical challenge. Do we have all the technology we need to make this happen? And if not, what would be some of the technical problems we need to solve?
We have most of them, but we don't have all of them. And the need for technological innovation is acute, but not so much in order to achieve net zero. We can probably do that with the technologies, or get close to it with technology that we currently have. But if we wish to do so without causing very significant environmental problems, and particularly for people who are least able to afford it, then the need to make things better and better, more affordable, more useful is acute. And the sort of skills that you need, they're right across the board, and they're not just STEM skills. But there are urgent needs to make better solar panels, more efficient solar cells, and people are doing that, to make better batteries, to make better electric cars. That's already a massive global effort, and that only needs to accelerate. But we need to think of new ways to finance projects so that the risk is acceptable to investors and that the vulnerable don't suffer the consequences of those kinds of investments. So there's a lot of innovation right across the whole sector. And personally, I think that's a tremendously exciting thing, particularly for people who thinking about getting into it.
Great, thank you, Michael. One thing that is often discussed as necessary to get us to net zero is carbon capture and storage, storing carbon in the ground. And Vera, you've spent a large part of your career studying what's underground, and you've shown us that the vast majority of the Earth's carbon is actually found in sediments, soils, and rocks. So in what ways can we actually store the carbon in the ground? Can we actually do it, and can we do it permanently?
Yeah, so I guess we tend to think of the rocks under the ground as being quite solid, but actually there's a number of rock types that are almost act as sponges, and these occur, not too far from the surface. So I suppose the principle is those same rocks that were almost a sponge with pores that once had oil and gas in them that we've now exploited, is to actually refill those kind of drained sponges with some of the CO2, either in gas or liquid form, to help store the carbon, because we know it can be stored in the earth for tens of thousands of years, even millions of years, until eventually it's subducted. And there's also been some work where people have been experimenting with injecting liquid CO2 underground, and it reacts with basalts and precipitates minerals like calcite. So it's not even, I think, as Michael was alluding to, there's so many interesting technologies being developed at the moment trying to address just that, because we know, as you mentioned, Todd, the earth and the rocks itself do represent a wonderful storage unit of carbon. So if we can just help it get back to where it was, I think that offers a really useful short-term solution to help reduce the CO2 in the atmosphere.
Great, thanks, Vera. I guess in the past, there's been, through cycles of hot periods and ice ages, there's also been changes in carbon dioxide at the same time. So how has the Earth actually reduced its carbon dioxide concentrations naturally in the past? And is that something that we need to think about here?
So if we go back to the carbon cycle, the way the Earth's regulated its climate for billions of years, and one really efficient way to draw down CO2 is through rock weathering, and in particular silicate weathering. So there has been some research being done recently where we've added acids to rocks at the Earth's surface in order to enhance weathering, and that has proven as another effective way to draw down CO2. So if we kind of can tap into what the Earth has been doing for a long time, that can help. The other thing we know, as you mentioned earlier, trees, 50% of most plant biomass is carbon. So of course, if we can plant more trees, and in particular wetlands and swamps, where when that plant material dies, it's actually preserved as carbon because it's in an oxygen-free setting. I think that's another really way that naturally the earth can draw down that carbon and help reduce CO2.
Great, thanks, Vera. So, Andrew, when we reach net zero, and you spoke about this briefly, how will Australia's climate be different when we reach net zero? Will we still be getting more extreme weather events? Will we get more droughts, more floods? How about Victoria's climate? What can we say about this?
So this is quite a big unknown because most of our climate modelling has been focused on continuing greenhouse gas emissions, a warming world, and understanding the risks associated with that. Under net zero emissions, we have far less information to go off, but we think that Australia would slightly cool over time. It's unclear whether it get wetter or drier. So in terms of extreme weather events, we know in Australia that we experience really quite severe extreme weather events. We saw really bad floods just last year in Victoria, New South Wales. We saw bad fires a few years ago now, and with the possibility of El Nino coming, we may be heading for a warmer, drier period in Australia. We expect we'd probably see similar kinds of extreme events to these in a post-net zero world. But it kind of depends on our pathway to net zero as well. If we delay getting to net zero and continue to emit lots of greenhouse gases and warm the planet first, then we're going to be experiencing far more heat waves, and that would be for a long time to come as well. The other thing is, even under net zero emissions, we can expect to see continued sea level rise. So we are going to see worse coastal inundation associated with extreme events and just higher tides in general for centuries to come.
Great, thanks, Andrew. I guess even over the next 50 or so years, once we've hopefully met net zero, we're going to be in this environment with significantly higher CO2 than we had 100 years ago, warmer temperatures than we had 100 years ago. So Vera, I guess you've looked at past climates where it has been warmer than it is now, with higher CO2 levels than it is now. And how can we expect plants to respond over the next century in an enhanced CO2 environment based on what you've learned from past climates?
Yeah, so plants will respond if they can by moving. So we know even from glacial interglacial cycles over the last 20,000 years that plants can disperse about 500 meters a year. That's the maximum rate they can disperse. So this is when the rate of change becomes really important. If we can slow it down enough, they may be able to either move to higher altitudes where temperatures are cooler, or maybe move further south. In order to cope. That's what they did in the past. The things that were going the equator moved to the mid-latitudes, and things in the mid-latitudes moved to the pole. So the plants will attempt to move to where conditions most suit their preferences. But of course, this becomes problematic when it comes to agricultural crops and things like that, because those plants don't generally have very high dispersal capability. So there is a lot of problems. And the other thing is, there's obviously lots of man-made infrastructure now in the way. So will plants be able to move as they did in the past? So there's something called assisted migration. Some people are thinking of bringing in to help prevent biodiversity loss in plants, where we kind of move them to where we think they'll be able to prosper in those new rainfall and temperature requirements. So yeah.
Interesting. Thanks, Vera. Okay, Michael. One of the big challenges we see in Australia is that we have a lot of resources that we've been using as a country and exporting as a country for energy use, carbon-intensive resources like coal. What will happen when we reach net zero and we've reduced our usage of those resources significantly, or even if we're ambitious and think about when we're net negative, and hopefully we get to net negative, what will happen to our energy exports? Because that has significant flow-on effects for our economy.
It does indeed. That's a very good question, Todd. Right now, we export thermal coal, metallurgical coal, and LNG overwhelmingly, and we export a lot of other stuff, iron ore, uranium, and so on. But in terms of creating offshore emissions, the big three are thermal coal, metallurgical coal for steel making, and LNG, liquefied natural gas. As they're all oxidised offshore, they create about 1,200 million tonnes of CO2 today, compared to 600 million tonnes that we create domestically. And that includes agriculture domestically. Now, so twice the amount of emissions are created from Australia's energy sector offshore than are created domestically. So it's a very big problem. And it's all, and by the way, the energy that we export is about 2.5 times the amount of energy that we consume domestically. So it's both a very big problem, and that's why I mentioned solving the export challenge and making it net zero is an essential part of the challenge, because as Andrew will tell you, where the CO2 comes from before it goes into the atmosphere is immaterial. The fact that it's in the atmosphere is what matters. So we really have to take our exports very seriously. But here's the thing, we're 1.5% or so of the global population and global GDP. There's a lot more people outside Australia than inside, and there's therefore a lot more money outside Australia than inside. So the trillions of dollars that we need to spend, partly to solve the export challenge, should be foreign investment in Australia's energy system, so that we can sell people all around the world the energy that they need. Australian energy exports have gone up by about a factor of 3 or 4 since 1980. So it's a very interesting question as to whether or not, as we decarbonise, whether they'll continue to grow or fall or stay the same. We don't know. It's a very, very uncertain thing. But if the world continues to grow and to become wealthier, and we want many people in the world to become wealthier, because a lot of people are not wealthy today. So as they become wealthier, their energy consumption probably will rise. And we want that to be clean and affordable energy, and hopefully we can sell some of it to them. But it's a very important problem, but also a tremendous opportunity for the nation.
Thanks, Michael. And we've now exhausted all the questions that I was going to ask you all. So I'm now going to move to the questions that we're getting from the online audience. And we're getting quite a few, but I encourage those of you who are online to continue to post your questions in the Q&A. I think my first question is actually for Vera, and going back to your presentation, and you were saying what you showed was our ice age was only about 4 degrees cooler than our current day long-term 100-year average. Is that correct? And why does 4 degrees matter so much?
That is correct, and that's based on some of the oxygen isotope and carbon isotope data from fossils, which is good. But I think that matters because what's happening, I suppose, what we keep coming back to today is we're talking about rate of change. And what's superimposed over the last 1 to 2 million years, where we've had this, glacial interglacial trend where temperatures have kind of decreased, and because we're kind of fluctuating up and down, that's why it kind of minimizes the effect of it, because it's kind of averaging it out. But it is a real trend, and that's what I think it makes it even more phenomenal that we've been able to reverse this cooling trend that we've had the last 1 to 2 million years so quickly. So yes, it is a real trend, and I think if anything, it is almost not even quite showing the full extent of how cool it did get during that time.
That's really interesting, and I guess that rate of change question keeps on coming up, and I guess passing this question to Andrew around the rate of change. Even if we reach net zero, and you spoke about this earlier as well, and the oceans continue to warm, will we still see these changes in weather events, coral bleaching, and how long will that continue for if we achieve net zero? How much is locked in?
Yeah, that's a really good question. And it depends a bit on our emissions pathway. So if we pass through net zero straight to net negative emissions and actually have quite deep net negative emissions where we're taking up more carbon than we're emitting as humans, then we would be cooling the planet, and the oceans would start to cool shortly after. But I mean, I say the oceans, but different parts of the oceans respond differently. So the Southern Ocean is expected to warm for quite some time. Areas experiencing tropical coral bleaching would probably cool shortly after net negative emissions were reached, significant net negative emissions were reached. But there's a lot of unknowns in terms of how our climate would evolve under net zero or net negative emissions. It's an understudied topic, just because the climate science community, up until very recently, has been really focused on the risks of a warming climate and continued greenhouse gas emissions.
So I guess it's not just net zero for Australia as well that's important here. And the question has come through as well. Australia may be able to achieve net zero by 2050, but what are the chances of actually achieving global net zero by 2050? And I'm going to pass that question to Michael, if you'd like to answer that one.
I don't think it's something that we can't model or have a view on. It's very difficult. I mean, 2 years ago, if we'd asked if there was going to be a war in Ukraine, we probably would have mostly said no. So, and that's had very major effects on the costs of energy all around the planet. So I don't think it's an answer that a question that anyone can credibly answer. So I won't even attempt it. But getting back to the Australian question and whether we can do it as a nation, when I see these very big numbers and very big challenges, I keep referencing it to things that I consider meaningful references. So that 2.5 times, I should say, of our domestic energy that's sent offshore in exports, we've created one of those 2.5 times in the last 5 to 10 years as liquefied natural gas exports. So if I said to you, I can do one thing, I've done one thing in the last 10 years, can you do 3 things in the next 30 years, Todd? And by the way, it's more urgent now than it ever has been. You should be able to say to me, of course I could. So we have done this, so therefore we could do this because we now know it's urgent, as we didn't know, say, as acutely 10 or 20 years ago. So I'm optimistic because we forget what extraordinary things we've done as a civilization over the last 150 years, let alone the last 10,000 years, or we didn't have a civilization 50 million years ago, Vera, but we've done some extraordinary things, particularly since the Industrial Revolution.
Thanks, Michael. I guess I've had another question, which I'm going to also pass to you. And one thing that we desperately need to do to move to net zero is the use of batteries, right? Batteries come up, and short-term energy storage comes up a lot when we shift to a discussion of renewables. Are there assumptions there about how batteries are produced? It takes a lot of energy and a lot of resources to produce batteries. Is the idea that eventually batteries themselves will be produced with renewables, and the byproducts of those batteries less damaging to the environment than using fossil fuels? Do we have a good understanding of this?
We have a reasonable understanding of it, but that's a very big question and a very important question. So if you look at the resources that go into making a lithium-ion battery today, there are many that are of varying degrees of availability. So cobalt and lithium are the two that are most commonly discussed. But the actual geology of resources, which other people on this call know a lot more about than I do, when you look for stuff much more seriously, you tend to find a lot more of it than you think you have. That's one thing. So our understanding of what reserves we have all around the world for lithium, for example, has changed a lot in the last 5 years. And this country's got a lot more lithium today than we thought we had 5 or 10 years ago. So these things are moving all the time. Also, very interestingly, one of the founders of Tesla, I've forgotten his name, has moved and started up his own company, which is battery recycling. So a lot of the material that are in degraded lithium-ion batteries at the end of your EV or the end of your phone's life are by definition a very rich source of the primary materials that can go into future batteries. So there's a tremendous innovative opportunity there for the recycling of battery components. But we're seeing needs for an enormous amount of battery storage. So we're talking here about hundreds of gigawatts of renewables domestically compared to 25 gigawatts we have today, and thousands of gigawatts to service the domestic export sector compared to 25 gigawatts we have today. But we're also talking about 50 to 100 gigawatts of battery storage needed in Australia and tens of gigawatts of pumped hydro. So there are very, very big resource needs, but recycling, innovations in the supply chains, all of these things, we get surprised all the time how good we can get at things by doing them.
Great, thank you, Michael. And so Michael was just using the word geology and talking about what's in the ground. And Vera, you showed some graphs which showed temperatures going back millions of years. And you talked briefly about how fossil plants are used to understand past temperatures and past climates. What are the other techniques that are often used? And we've had a couple of questions about that from the online audience, about what techniques are used to work out what happened 10,000 years ago, 100,000 years ago, a million years ago.
Yeah, so we use a whole range of different techniques. A really big field is geochemistry. So we can actually use the ratios of different elements to tell us a lot about temperature. We can use the amount of certain minerals in the soil to tell us how wet or dry it was. And that's actually a really important topic when we talk about carbon. A lot of carbon's still in the soil. So we can even look at changes in rock color through time as a proxy for whether it was wet and drying, whether the soil was oxidizing and reducing carbon. So that is the few of the techniques we can use. But in general, we do look back at the rock record and just try to look at the fossils to infer from that what the climate was like. And again, the mineralogy, the chemistry. So there's lots of fun tools we can use to reconstruct temperature. But a kind of fun emerging field is looking at the chemistry of certain parts of like leaves and pollen. And there's some really interesting experimental work where we're actually growing trees under elevated levels of CO2, measuring their chemistry, and then using that to try to deduce how temperature has evolved through time. So it is definitely an emerging field. And I think there's a lot of exciting things to come that will just help us understand even in more detail how the Earth's climate has changed over time.
Thanks, Vera. That's really interesting. I'm going to switch gears a little bit now and pose a question to all of you, because you're all university academics who've done training at universities in areas that are relevant to this topic of achieving net zero and what's going to happen in net zero. So it'd be great, and we've had this question from the audience, what courses, what training should people do if they're interested to be part of the growth and assisting in the future of net zero? Who wants to go first? Andrew, you can go first, then Michael.
Well, I think Michael highlighted how we need lots of people working on this problem. And I think, it's people with quite diverse skill sets as well. So I teach into the first year science subject, Today's Science, Tomorrow's World, which all science students take. And we're trying to prepare students with an understanding of climate change and the challenges of net zero, reaching net zero emissions, kind of in recognition of the fact that no matter what discipline or background you're really focused on and what major you want to take, this is kind of the challenge of our times. And it's a challenge that requires lots of different skills across engineering, science, technology, and maths.
Thanks, Andrew. Michael, would you like to add to that?
Well, I understand there are other universities in Australia, but the Bachelor of Science is a good start, of course, and Andrew's one of our star lecturers in first year, as you said. But to Andrew's point, this is a very, very diverse workforce. there's even hairdressers who work exclusively in the energy sector in Australia, right? So project managers, lawyers, financiers, many different types of people. Having said that, the number one most popular job we're projecting is electrician, unsurprisingly, if we're going to be electrifying the nation, right? But many different types of jobs. But if I were leaving school right now, a technical trade or a STEM career, and I'm showing my bias, and Moira will be chuckling, I'm showing my bias a bit here, looks to me to be a pretty good thing to do.
Thanks, Michael. Vera, anything to add to this?
I just think the more diverse a background of people we can get getting into this field and solving this problem, the better position we'll be in as well. So whether it's your expertise or in your own background, I feel like we can all really play a role to play. And I guess as a geologist, I think, of course, we have a role to play as well. And I think the more disciplines we can bring together, even looking at the panel tonight, the more kind of insights and perspectives we can gain. So hopefully all our students coming through it at the University of Melbourne do get that broader, I guess, understanding of climate change in a range of different subjects we teach, just to try to tackle this project in all our different disciplines.
Thank you, Vera. Okay, so another question for the entire panel. We're in a growth economy, and we often talk about growth being good. Is that inconsistent with what we need to achieve here to achieve net zero? But I guess along that same point, if we are in this, continue to be in a growth economy, what should we be doing as individuals, but also what should corporations be doing to continue to grow, but also achieve net zero? It's a tough question. You can go from an individual standpoint or a corporation standpoint.
I'll have a crack at it, Todd, and it's a very important question. You're dead right. So it's pretty obvious that on average in Australia, we consume more energy, a lot more energy than we need to. If you look at any indicators, for example, life expectancy, body mass index, all of these things, compare it to, for example, other wealthy countries like Japan or other places, we consume per person almost twice as much energy as the average Japanese person, and they live longer than we do on average. So there's tremendous opportunities for us individually to consume less energy. That might be not driving your car to work every day. It might mean riding your bicycle more often. It might be doing all sorts of things in your homes. It may just be consuming less food and eating less meat, for example. So there's lots and lots of things we can do individually. And that's a tremendous opportunity, because if you eat less meat and you do more exercise, guess what? You're healthier, you're happier, and you live longer, and you spend less money. So you actually get wealthier, healthier, happier by leading a more balanced life. So there's a tremendous opportunities for individuals to do many things which are in their own interests, as well as in the climate's interest and the environmental interest. By the way, we need less farmland, we have fewer animals, all of these other ecological benefits as well. So that's a very, very important thing, that we as individuals should consider ourselves and are empowered to actually make very measurable changes. It's not good to just see this as a problem to be solved by government and be solved by regulation of companies. But government does need to improve, of course it does, enormously, but also businesses, guess what? They respond to consumers and consumer preferences. And if we individually make it really clear what we do want to buy and what we don't want to buy, businesses will change and are changing already. So I see this as an opportunity for happier lives, healthier lives, longer lives, lighter touching on the planet lives, and that has to be led by the community, not by government and not by companies.
Right, that's an excellent answer, Michael. Thank you. Now, we have reached the end of our allotted time, but I'm going to use my chair's prerogative to go 2 minutes over. We started with the question, the title of this presentation of this lecture was carbon in our atmosphere, is it all bad news? And I didn't want to leave this with a bad news story. I wanted to leave this with a story of hope. And so I'm going to ask each of you just to give me a brief answer, brief sentence on hope. What gives you hope in this area of achieving net zero? Vera, do you want to go first?
Sure, I think we can turn to the past to give us hope. We know the Earth in the past has experienced times of really elevated CO2, and it did its job to draw it back down and cool the planet. So if we turn to the past, we know the Earth's done this before, we can do it again, and we can help it, reduce down the CO2. So yeah, I turn to the past for my hope.
Thanks, Vera. Andrew.
Yeah, I agree with Vera, and I would add that, yeah, we know what we need to do to tackle this problem. We have a lot of the technologies already. We're not fully utilizing them yet. So we know what we need to do. We have a lot of the technologies we need to get towards net zero. And yeah, I think there's exciting prospects for the future.
Great, thank you, Andrew. And Michael.
I agree, and it's very, very important. 25 to 30 years ago, I was an undergraduate, Todd, and then we had no internet. Nobody had a mobile phone. We were starting to get the internet. Melbourne University was the first place in Australia to have the internet. And think about how the world has changed since then. That's what's ahead of us over the next 20 or 30 years. And that tremendous innovative capacity is something you take for granted while you're doing it and have done it. But it's our historical, extraordinary achievements gives me tremendous hope for what we can do.
Great, thank you, Michael. On that note, I'm going to thank our three panelists for an exciting and interesting conversation and thought-provoking conversation for the last hour. Thank you to all of our guests who joined us online and those who will watch this, watch the recording later. So I wish you all a good evening and close the lecture now. Thank you very much.